Okay, so prime factorization. What did the theorem talk about? Basically that every integer greater than 1 is either a prime itself or a product of 2 or more primes. We discussed this theorem, went ahead to prove that. There are theorems which further develop on this theorem. For example, the theorem of unique factorization. It goes on further to say that also all those integers greater than 1 which are not primes themselves, that is, which can be expressed as product of 2 or more primes, can be expressed in such a manner that the product will be a unique combination. That is, if you look at these examples, for example, 8 can be expressed as the product of these 3 2's, that is 2 cube, all right? 2 multiplied with 2 multiplied by 2. And the theorem of unique factorization tells us that this factorization, this prime factorization is going to be unique. That is, you won't be able to come up with a different combination of prime numbers for the product to represent 8. 8 will be, if in order to represent 8 as the product of prime numbers, this is the unique. This is the unique and the only one and only case that you can use for in order to represent it using prime numbers. If you're only using prime numbers to express 8, right? So it's going to be exactly that. Even if you use some other composite number here, let's say you use 2 and 4, but ultimately 4 is 2 multiplied with 2, right? So the unique factorization basically tells us that 8, when it's broken down into the product of primes, that product, that combination of primes will be unique and it will only represent 8 and only 8, all right? And this combination will be unique. Whatever else, what other combination that you can come up with using another composite, remember that that composite can also be broken down into primes. So it ultimately goes down to the same thing. It's the same one combination, expressed in many different ways, but it's the same one combination. That is what we mean by the theorem of unique factorization. That is, for any integer that is greater than 1, it's either going to be a prime, and if it's not a prime, it's going to be a product of primes, and such that the product will be unique up to ordering, right? However, we're not going to go ahead and prove this one because this one is very complex to prove. However, we'll still look at an application of this proof. A theorem, no, an application of this theorem, sorry, a theorem that builds on this idea, the idea of unique factorization, it builds on that idea. So this theorem is a derivation of this idea of unique factorization, indeed, all right? So where it says that if n is a composite, that is for all integers greater than 1, which are not primes themselves, if n is a composite, then n, the integer n, has the prime divisor p such that p is less than or equal to square root of n. That is, every integer n, which is a composite, every composite integer n will have at least one prime divisor p such that p is less than or equal to square root of n. That is the theorem. That is what the theorem claims. And we'll go ahead and prove this theorem very easily using the prime factorization theorem we have already, all right? So now, since n is a composite, based on the prime factorization theorem, what can we say about n? It can be expressed as a product of 2 or more primes. Can we not say that, guys? If n is a composite, can we not say, based on the theorem 1, based on prime factorization, can we not say that if n is a composite, it can be expressed as a product of 2 or more primes?
Yes, ma'am, we can.
Yes, ma'am, we can.
Okay. If we can do that, indeed, in that case, let's talk about the least case first of all. It can be expressed at least as a product of at least 2 primes, right? At the very least, there will be 2 primes there in the product. It can be expressed as a product of 2 or more primes. So in that product, we can say that at the very least, duita prime to thakbe. Je product use korbo to represent this n. Oi product at the very least duta prime to thakbe. At least 2 or more, right? So at the very least duta to thakbe. Now, these 2 primes in the product, if these 2 primes were greater than, if both of these 2 primes were greater than square root of 1, sorry, if both of these primes were greater than square root of n, if both of these primes were greater than square root of n, think about the product of these 2 primes. these two primes that we are saying will be there in the product. At least two to thakbe, তাই না? So at least দুটা prime in product এ থাকবে. So these two primes, if both of them are greater than square root of m, what happens to the product? Will the product be equal to n? Square root of n multiplied with square root of n. Just square root of n whole square. What is that, guys? It's just n. Now, if these two primes, each of them are greater than square root of n, then the product will also be greater than n as well, right?
Yes, miss.
Okay. So in that case, it's not really expressing the composite n at all, right? So we are trying to represent the composite n as product of two or more primes. That is what the first theorem says, right? If n is a composite, it must be expressed as it must be possible to express it as a product of two or more primes. However, if at least two of these primes are greater than square root of n, then it's not going to be possible. It's not going to be possible to express it. It's not going to. The product is not going to represent n, right? Basically, it doesn't agree with the first theorem. It doesn't agree with the first theorem because if those two primes are greater than square root of n, the product becomes larger than n already. So theorem 1 is violated. So in that case, we can say that there will be at least one of these primes which will be less than square root of m. So a product, the composite, the number n, representing the number n with the product of primes, in that product, there will be at least one prime which is less than square root of m. সবগুলা যদি square root of n এর থেকে বড় হয়, সবগুলা prime, all the primes in this product, if they are greater than square root of n, then obviously it's not going to equate up to n. As you can see, it will equate up to a number greater than n. So in that case, what is the obvious conclusion from here? That at least one of the factors in the product, one of the prime factors in the product will be less than or equal to square root of n. Otherwise, it won't work. Okay, at least one. So that is what the theorem claims, that the composite number n has a prime divisor p such that p is less than or equal to square root of n. And that is what we have proved here. We did it by a proof using a proof by contradiction, right? So we first assume that, okay, what happens if the prime factors are greater than square root of n? Mane p less than equal to square root of n or opposite key, p greater than square root of n, right? So we assumed, what happens if the prime factors are greater than square root of n? If the prime factors are greater than square root of n, we see that we get a number that is larger than n. That is, it doesn't equate up to n, which must mean that at least one of the prime factors here must be less than or equal to square root of n. Otherwise, it won't work. সবগুলো যদি square root of n এর থেকে বড় হয়, তাহলে প্রোডাক্টটা তো ডেফিনেটলি n থেকে বড় হবে. So at least one must be less than or equal to square root of n. Is that part clear? Is this clear, guys? The proof?
Yes, miss.
Okay, pretty straightforward though. Okay, now an application of this proof. So, sorry, this theorem, an application of this theorem. So we can use this theorem to prove whether a number is a prime or not. So we have to show that 101 is a prime. Again, we'll do a proof by contradiction. We'll start by assuming the opposite, and from there, if we can see that it gets to a contradiction, we can say that our assumption was wrong. So the alternative path must be correct, and the alternative path is this: 101 is a prime. So let's get to it. The opposite of 101 is prime is what? That 101 is a composite. If we start by that assumption that 101 is a composite, if it's a composite indeed, then based on the theorem of prime factorization, it can be expressed as a product of two or more primes. Further, based on this theorem, if it's a composite, if 101 is a composite, then there's at least one prime divisor of this number such that that divisor is less than or equal to square root of n. So we will use this theorem in order to prove that 101 is a prime. All right. Now, if 101 is a composite, see, if 101 is a composite, in that case, 101 has at least one prime divisor, which is less than or equal to square root of 101. Now, what is the square root of 100? Guys, square root of 100, what is that?
10.
10, exactly. So the square root of 101 will be somewhere around 10, 10 point something, right? So all the primes that is less than or equal to the square root of 101, what are those? first of all, think about all the numbers less than all the integers less than or equal to the square root of 101. It will be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. And from here, what are the primes which are less than or equal to the square root of 101? 2, 3, 5, 7. But clearly 2, 3, 5, 7, none of them can divide the number 101. Divide bolte ami ki bujhachi? The remainder has to be 0. So none of these can divide the number 101. Hence, based on this theorem, we can say that 101 is a prime. All right. Very silly and straightforward, just to show you an application of this theorem. All right. Okay. So finally, we'll talk about the theorem which claims that the total count of prime numbers is infinite. That is, it's not possible to count the total number of prime numbers. All right, there are infinite prime numbers out there. This theorem, I'm quite sure at least some of you have come across this theorem previously and maybe have come across the proof of this theorem as well. Here, we will prove it by using the ideas, the definitions that we've studied in divisibility and primes. All right. Primes is so far G-shop concept we've studied and divisibility. We'll combine both and we'll prove this theorem by combining both of those. All right. So, excuse me. So let's say we'll start with, we'll prove this using a proof by contradiction. So let's say that there are finite number of prime numbers. Proof by contradiction is etai kori, tai na? Jeta proof korte bole setar opposite ta claim kore, we'll so show that it gives a contradiction. So what is the opposite of this claim that there are infinite prime numbers? The opposite is there are finite number of prime numbers. If the total number of prime numbers is finite, if the count of the total number of prime numbers is finite, in that case, is it not possible to have a list of all those prime numbers? It is the finite, তাই না? Finite মানে কি? আমি একটা list বানাতে পারবো of all the prime numbers, right?
Yes, miss.
So if there are finite number of prime numbers, then we can collect all the prime numbers and have a list in an ascending order. P1, P2, P3, P4, P5, P6, and so on until Pn. কতগুলো prime আছে এখানে আমরা জানি না, but finite. So একটা লিস্টের মধ্যে সবগুলো prime রাখলাম. That is, all the prime numbers are in this list. We create a list of all the prime numbers. Since the count is finite, it's possible to do that, right? Based on the assumption. Since the count is finite, it's possible to do that. We can have a list like that. So we have all the prime numbers in this list. So that is, there are no prime numbers outside of this list, based on the assumption. In that case, the number that you get from the product of all of these primes plus 1, that is this number. The product of all the primes in this list plus 1. What can you say about that number? Based on the assumption, is this going to be a composite or a prime? A number can either be a composite or a prime, right?
Yes.
Yeah.
We are showing it is a composite function, so it will be a composite.
We are showing it as a what again? Composite?
Yes, miss. We are showing it as a composite function.
How?
Composite number.
How? How are we showing it as a composite number? Think about that.
It's like if any of the divisors are not prime, then it will be a composite function.
But we haven't said anything like that any of the divisors are not prime or anything like that. We haven't said anything like that. ওই জিনিস তো আমরা এখনো কিছু বলিই নাই। মানে yeah, well, based on the assumption, we have to say that okay, this is composite, but I'm not sure on what you are saying, that there are no prime divisors of this number. Is that what you're saying, though? That there are no prime divisors of this number? Or are you saying that there are prime divisors of this number?
There are no prime divisors of this number.
Of this number. Why are you saying that again, Arshad?
Yes, because we are adding 1 to it.
Adding 1 to the product of all the primes. Okay. Yeah, that's one possibility. So if there are no prime divisors of this number, in that case, is it a composite? তুমি তো উল্টাটা বললা না? What does the theorem tell us? the prime factorization theorem bolo, by theorem bolo, jetai bolo, what does it tell us? It tells us that if the number is a composite, if it's a prime, then it's a prime. If it's not a prime, that is, if it's a composite, it can be expressed as the product of two or more primes. That is, it will have prime divisors, right? But you're saying that it will not have any prime divisors.
Acha, miss. Yeah, miss.
Okay, so that is our contradiction actually. I mean, we've already arrived at the contradiction. So that is the contradiction. So even though you went to the wrong conclusion, but still, when you get that, see, that is the point here. But okay, more on that later. But based on the assumption basis jodi just boli, tahle a number ta has to be a composite, right? That's where the problem is. You see, the number has to be a composite based on the assumption. If there are finite number of prime numbers, total number of prime numbers jodi finite hoy, ami to একটা list create করলাম, তার মানে কি এই লিস্টের বাইরে আর কোনো প্রাইম নাম্বার নাই। একটা নাম্বার তো আইদার প্রাইম হতে পারে আর কম্পোজিট হতে পারে। এই লিস্টের বাইরে যদি আর কোনো প্রাইম নাম্বার না থেকে থাকে, তাহলে this number is what? Outside of this list, right? This number is definitely going to be greater than Pn. We have the product of all the prime numbers and then plus 1. So obviously this number is going to be outside of this list, right guys? আমরা তো সব prime number এখানে list করে ফেলেছি according to our assumption. So if all the prime numbers are in this list, then this number must be outside of this list, and hence this number must be a composite. It must not be a prime. যদি প্রাইম হয়ে থাকতো তাহলে তো ওই লিস্টে থাকতো, right?
মিস
Does it make sense so far? Yeah.
মিস এইখানে যে n এর আমরা মানে +1 করতেছি, এখানে তো if you don't even do +1 আমার তো এটা অলরেডি একটা কম্পোজিট হয়ে যাবে if you multiply like all the prime numbers.
Yeah, we will obviously, if we multiply all the prime numbers, we'll get a composite, but we are not trying to prove that. We are trying to prove that there are infinite number of prime numbers. Infinite number of composite numbers আছে কিনা এটা তো আমরা prove করার চেষ্টা করছি না, right? We are trying to prove that there are infinite number of prime numbers. Think about it. এই যে এই +1 অ্যাড করার কারণে, যে আরশাদ যেটা বললো, যে এই প্রোডাক্টের সাথে +1 অ্যাড করার কারণে আমরা কি বলতে পারি, যে this number will never have a prime divisor. Why? Because এই যে এই প্রোডাক্টের সাথে তুমি 1 অ্যাড করেছো, তাহলে সবগুলো প্রাইম নাম্বার যদি এই লিস্টে থাকে, all prime numbers are in this list and all prime numbers are already here as a factor, আর এর সাথে তুমি 1 অ্যাড করেছো, সো এই নাম্বারটাকে তো এই কোন এই যে এই লিস্টে কোনো প্রাইম নাম্বার দিয়ে ডিভাইড করা পসিবল না। That is, you're saying that this number ultimately is a prime itself. However, have you included that in the list? No, it's outside of that list. Okay, let's include this one in the list. Let's say there is Pn plus 1. এই যে Pn এর পরে আরেকটা আছে Pn plus 1, which is this number. তারপর আমি বলতে পারবো যে the product of all these primes again and then plus 1 again. Do that. You see the point, you see the contradiction, it's already there. Even if you don't see that, we'll break it down further, so don't worry about it. First, let's again start from scratch. So since we are starting with the opposite assumption, I mean like assuming the opposite of the claim is that there are infinite number of prime numbers. We'll assume the opposite, that there are finite number of prime numbers. Jodi total number of prime numbers finite hoye thake, tahle ekta list banano jabe of all the prime numbers. We can have a list of all the prime numbers starting from P1 until Pn. So সবগুলো prime number এই লিস্টে আছে. Then we are saying that let's take a number n, which is the product of all of these primes plus 1. A number tato, it's obviously after, it comes after Pn, that is, it's outside of this list. And if it's outside of this list, it must not be a prime, because আমরা তো সবগুলো prime কে already list count করে ফেলেছি, so it must not be a prime. It must be a composite. Now, if it's a composite, whether it has a prime divisor or not, we'll think about that later, all right? If it's not clear to some of you guys, we'll think about that later. But for now, if it's a composite based on the theorem of prime factorization, if it's a composite, what does it say? It can be expressed as a product of two or more primes. That is, it must have a prime divisor. If it's a composite, it must have a prime divisor, right? Theorem, prime factorization theorem basis আমরা এটা বলতে পারি যে এই composite numberটা একটা prime divisor থাকা উচিত. So that prime divisor will be from this list, right? এটা তো আমাদের, this is the list of prime numbers. All the prime numbers are here in this list. So if this number does have a prime divisor, then it will be from this list, which is Pj, all right? Let's say Pj is one of the prime numbers from this list, which can divide the number n. So far, are you understanding what I'm saying? We're just proceeding based on the assumption. আমরা কিন্তু assumption এর basis এই আগাবো. we will get to a contradiction. Some of you should already notice that this is a contradiction, that a product এর সাথে 1 add করলে how will you get a prime divisor of this number? That is already a contradiction. But ওই জিনিসটাই হচ্ছে কি আমরা will break it down and show it using the concepts that we have learned so far. মানে this should already occur to most of you since you have used primes many times in your lives. So this should occur to you, but we will still break it down and prove it using the concepts that we have learned so far. All right. So এই যে এটা যদি এখানে এই লিস্টে যদি সবগুলো প্রাইম থাকে, এই লিস্টের বাইরে যদি আর কোনো প্রাইম না থাকে, and it's possible to do that since we are assuming that there are finite number of primes. এটা হলে this number must be a composite. এই নাম্বারটা it's outside of this list. Obviously, it's greater than Pn. So this number is not going to be a prime. And if it's a composite, then based on the theorem of prime factorization, which we have already proved, based on that theorem, this number, if it's a composite, it must have at least one prime divisor, right? It must have at least one prime divisor. Two, actually. It can be expressed as a product of two or more primes, right? So it must have at least two prime divisors. So let's talk about one. Ekta prime divisor jodi thake, that prime divisor will be from this list, because in our assumption, we have claimed that all the prime numbers are in this list. So the prime divisor, which divides this number n, will be from this list, right? Guys, does that make sense?
Yes, miss.
Okay. If it's from this list, then let's say Pj is that prime number, where the index j can be any number from 1 to n, obviously, representing any possible prime number from this list, which can divide n such that the remainder is 0. Okay. So now that n is a composite, we can say something like that, that it has a prime divisor from there. Now this same prime divisor, j prime divisor ta n ke divide korte parbe, whichever that is. The divisor of n, the prime divisor which can divide n such that the remainder is 0, that same prime number ta, should it not be able to divide the product of the primes, just the product of the primes? Because that divisor is there as a factor in this product, right? A divisor ta to a product er moddhe ekta factor hisebe thakbe, right? It's from this list. And this is the product of all the primes. So the divisor, the prime divisor which divides the number n, will also be here in the product as a factor. So does that not mean that the prime divisor, the same prime divisor, will be able to divide this product as well, guys?
Yes, miss.
Okay. So the prime divisor, the same prime divisor, can divide the number n and the product of all the primes. We've established that. Now, remember from the things that we discussed when we were talking about divisibility, that if the same divisor divides two different numbers, then it can divide the sum of the two numbers as well. Or in other words, the difference of the two numbers as well, all right? So let's say if the same divisor A divides the number x and the same divisor A divides the number y, then it should also be able to divide the number x minus y, right? So same goes here as well. If the same prime divisor Pj divides n and the same one divides the product, then it should be able to divide the difference of the two as well, right? n ke alada bhabe divide korte pare, এই যে এই প্রাইম গুলোর প্রোডাক্ট কে আলাদা ভাবে ডিভাইড করতে পারে, সো এই দুটার ডিফারেন্স কেও ডিভাইড করতে পারা উচিত, রাইট? দ্যাট ইজ ইফ ইউ ডিভাইড n by pj, you get an integer as the result. Here as well you get an integer. The difference of the two integers will also give you an integer, so pj should be able to divide this difference, right?
Yes,
Guys, okay. Now what is the difference? n থেকে exactly 1. However, what is the only number that can divide 1 where the remainder is 0?
1.
1 itself. However, we are saying that pj is a prime number and prime numbers are all greater than 1. But 1 এর থেকে বড় কোনো integer, there is no such integer which is greater than 1 which can divide 1 and the remainder will be 0. Is there? No. So pj dividing 1, the remainder being 0, is it possible if pj is a prime number?
No, miss. So it proves
No.
that it is contradictory.
Exactly. It proves that our assumption is completely, totally, utterly wrong. That means, since the assumption is wrong, the only alternative path is that the total number of prime numbers is infinite. All right? It was clear. It should be clear to some of you right from the start that এই নাম্বারটা তো দেখলেই বোঝা যাচ্ছে, এই নাম্বারটা তো দেখলেই বোঝা যাচ্ছে যে এটার কোনো প্রাইম ডিভাইজার থাকবে না, সবগুলা প্রাইমের প্রোডাক্টের সাথে 1 অ্যাড করেছি, এটা প্রাইম ডিভাইজার কেমনে থাকবে, রাইট? বাট মানে এটা যদি কোনো prime divisor না থাকে, based on the prime factorization theorem, then it must be a prime itself. But have we not said that we have already counted all the primes? We already have all the primes in this list, but this one is outside of that list. If you say that, okay, ma'am, নতুন একটা prime পাইলাম, ওটা এই লিস্টে add করি. But it still holds true for the next one. Again, you can say that, okay, এটাকে আমি add করলাম এই লিস্টে. Then again, you can say that, okay, আবার সবগুলোর product করো, plus 1 করো. Again, you get the same situation. So you will always have this scenario, okay? If you say that the total number of primes is finite, there will always be that one other prime. If you say that the total number of primes is finite, after listing the prime, in this format, you will see that there's always that one other prime, the next one. So which says that the total number of primes is infinite, right? Okay, any questions regarding this? All right, then. I didn't expect so. Pretty straightforward. This is a theorem, like I mentioned, that some of you might already have encountered already as well. The Euclidean theorem, the Euclidean proof of infinite number of primes. All right, but the reason we have used this theorem specifically is to show you the use of the ideas of that we have discussed, the definition of primes. We have used, see here, we have used the definition of primes and divisibility together to prove this thing. More important is the process. যে কিভাবে আমি এটা prove করেছি. Primer idea আর divisibility দোনোটা use করে we proved it, all right? So that you can replicate this process for some other theorem that you'd have to prove maybe, all right? So there you'd know that, okay, divisibility use করে, primes এর definition use করে, I can prove something. So for that reason, we have used this theorem here as an example. Now the Goldbach conjecture. So carefully look at this set of examples, all right? Here we have all even numbers, 4, 10, 16, 6, 12, 8, 4, 20, 8, 14, 20. All of these are even numbers which are greater than 2. All of these are even integers greater than 2. And you will see that every single one of these integers is expressed as the summation of exactly 2 prime numbers. They can be expressed as the summation of exactly 2 prime numbers, as you can see. And also, 20 পরে তুমি যে নাম্বারই আনো না কেন, as long as the integer is even and greater than 2, you will see that every example you bring in, they can be expressed as the summation of 2 primes. Okay, 22, 24, all of them. So this gives us the idea that every even integer greater than 2 is sum of 2 primes. This leads us to assume that, okay, based on this, maybe every even integer greater than 2 is sum of 2 prime numbers, right? However, it's not a theorem. Why? Because there is no proof of this. Remember the prime factorization theorem? We had these examples, right? These examples which gave us the notion that every integer greater than 1 is either a prime or a product of 2 or more primes. The examples gave us that notion. In fact, you can bring in any other integers, 3, 8, 12, 15 এর পরে যত integer চাও আনতে পারবে, and you'll see that every single one of those integers agree with this theorem. They will either be a prime themselves or they can be expressed as a product of 2 or more primes. Every single example you'll bring, you'll see that they agree with this theorem, obviously. However, the examples, are they good enough to prove the theorem? No. Using examples, you cannot prove something because the world of numbers is infinite. So example use করে কোনো কিছু proof করা যায় না. Example use করে simply you can say that, okay, it's a possibility, but you cannot prove it without any room of doubt. So that is this idea that every even integer is greater than 2 is the sum of 2 primes. This idea, there's no proof of this. So that's why we call it a conjecture. However, at the same time, there is no proof otherwise as well. That is, it against your kono proof nahi. That is why we call it a conjecture. Any example you bring in, you can think any example that you can think of in the number line, you'll see that as long as it's an even integer greater than 2, it can be expressed as a sum of 2 primes. You see that, right? So that's why it's a conjecture. That so far it hasn't been disproved. All examples that you can come up with tell us that, okay, the idea that we have here seems to be the right idea. However, since there are no proofs, it's a conjecture. It's not a theorem, all right? Just to give you an idea of what a conjecture is. and use the Goldbach conjecture. I think it's quite interesting. So anyway, with that, we end our discussions on number theory.